then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, Precalculus students. Welcome to lesson number 12. Here we go. Okay, today's lesson is on continuity. The first of a series of lessons on continuity. It may seem like a bit of a misnomer because really I'm going to be discussing discontinuities probably more than I'm discussing continuity. But in discussing discontinuities, at the same time talking about continuity, if you will. So again, this is a multi-day series, this investigation of continuity. And so first thing I would like to do is just kind of explain what we mean. And so when I'm talking about continuity here, we're going to be talking about continuity at a point. So there are three things you need to see for a function to be continuous at a given point. And those three things are as follows. So it reads a function f is continuous at c. So c is some value for x if the following three conditions are met. First, f of c is defined. Second, the limit as x goes to c of f of x exists. And third, those two things should be equal. So f of c should equal the limit of f of x as x goes to c. So those are the three conditions to be continuous at a point. So if you meet all three of those conditions, then the function f of x is continuous at the point x equals c. If any of those conditions are not met, then you are not continuous and you have what is called a discontinuity. And what we're going to do next is we're going to look at the different discontinuities from a graphical standpoint and what certain discontinuities look like. There are three discontinuities we look at: a removable discontinuity, a jump discontinuity, and an infinite discontinuity. So we're going to look at how those look from a graphical standpoint. So from today, we should be able to see a function and be able to tell at a given point if it's continuous or not continuous. And if it's not continuous, we should be able to classify the type of discontinuity that it has. So again, if these three items are not met, the function is not continuous at a point, meaning if the limit does not exist, you can't be continuous. If f of c is not defined, you can't be continuous. And let's say the limit exists and f of c is defined, but they're not equal, then you can't be continuous. So all those things you have to take into consideration. So let's look at some examples of discontinuities and the three different types of discontinuities we look at. All right, this first example is a removable discontinuity. So I need you to be able to recognize right now what a removable discontinuity looks like. And when I say this, I'm referring to the value at x equals -2. So at x equals -2, you have this little hole. So hopefully you can see that there's a little hole. And in fact, a removable discontinuity is called a hole, and it's also called a point discontinuity because it's just a little point that's missing. So there's just a little open circle here when x is -2 on the graph of this particular function. And whenever you see that, basically the whole function is pretty much intact, except you have this one little point missing, this one little hole on the graph. That's what we classify as a removable discontinuity. So this function has a removable discontinuity at x equals -2. And if we look at our three conditions, the one condition is not meeting is f of -2 is not defined. Remember, f of c should be defined for it to be continuous, where in this case, f of -2 is not defined. The limit exists. The limit as x goes to -2 equals -2. So the limit exists, but however, f of -2 is not defined. So therefore, it can't be continuous. And again, this is what a removable discontinuity looks like. Let's look at another discontinuity. So this is removable as well. And in fact, pretty much the same thing. And here it is right here. Here's your removable discontinuity. And we're talking about where x equals 1. So at x equals 1, you have a removable discontinuity here. And it's the same exact deal as the previous problem. The reason you have it is because f of 1 is not defined. The limit exists. The limit as x goes to 1 is 3, but f of 1 is undefined. And again, you see the little point, and there you have your removable discontinuity. Let's look at another. So on this graph, there are two discontinuities on this graph. There's a jump discontinuity here at x equals -1, and there's another removable discontinuity here at x equals 3. But this removable is different from the previous two we looked at. So I want to look at this removable discontinuity first for a second. Now, this is removable. How do we know? Because we see this little point when x is 3. We see a little point on x is 3. What is different, however, so we have this open circle here, but we also have a closed circle here. So in our previous two problems, we only had an open circle on a point, not a closed circle on a point. But it's still not continuous. But you may say, why? Because now you can say f of 3 is defined, and actually it is. F of 3 is -2. F of 3 is definitely defined. So it meets the first condition of continuity. The function f of c is defined. F of 3 is defined. And it actually meets the second condition of continuity because the limit of f of x as x goes to 3 exists. It's -1. The limit as x goes to 3 is -1. So it meets the second condition, but it does not meet the third condition because the third condition states that if f of c is defined, which it is here, and if the limit exists, which it does here, they should be equal, but they're not equal. Here, f of 3 is -2, and the limit of f of x as x goes to 3 is -1. So even though f of 3 is defined and the limit as x goes to 3 exists, they're not equal, so it's not continuous. And again, from a visual standpoint, if you just see an open circle where the point is, and more than you should see an open circle, but the rest of the graph all together, except at that little open circle. And I make that emphasis, and I use this graph that has both removable and a jump on it because sometimes people will confuse what's happening here and say this is a jump. So let me look at the jump over here at x equals -1 and then juxtapose these two situations. So this is a jump discontinuity here at x equals -1. And it's called a jump because you're on one part of the graph and it just jumps to a different value. And now you're on a whole nother part of the graph. So again, the whole function jumps to a different value. See, here at this removable, just one point, if you want to say jumped. So one little point jumped, but the whole function is still in the same place. Well, for a jump, the whole function jumps. So the function went from here and jumped to here. So that's what a jump looks like. Now let's see what conditions did it not meet for this particular function. So let's go through our three conditions of being continuous. The first one, does f of -1 exist? Yes, f of -1 is 2. So if you see a closed circle on the point, or just the graph is smooth on the point, like for instance, f of 4, like I don't see a closed circle, but f of 4 obviously is 3. So basically, if you don't see an open circle on the point, and even here at -1, there is an open circle, but there's also a closed circle. Here at x equals 3, there is an open circle, but there's also a closed circle. So if you see a closed circle or it's just smooth at the point, then the function is defined at the point. So f of -1 is 2. So, and I think earlier I said f of 4 is 3. I might have said that. Seems like I sound like I said that, but f of 4 is clearly 2. This is 2 here. From the line made me think it was a 3 perhaps. Okay, so f of -1 is 2, meets the first condition, but it doesn't meet the second condition because the limit doesn't exist. It's approaching 1 from the left and 2 from the right. So the limit doesn't exist. So this one, f of c was defined, but the limit as x goes to c did not exist. So that's what makes this non-continuous. And again, when you see the whole function jump from one value to another, could jump up, could jump down. If you see the whole function jump, that's a jump discontinuity. If you just see an open circle and then a closed circle somewhere else, that's going to be a removable discontinuity. Okay, our next guy. So this is another example of a jump discontinuity. And I think and I'm talking, of course, here where X is 1. I think it's quite obvious. It jumps to this value. You may see, well, why are you showing this particular jump discontinuity? So this jump is a little bit different from the previous jump because in this case, for this particular jump, two things occur. Two conditions are not met. One, f of 1 is not defined. Look, f of 1 is not defined. If you look at our previous jump, f of -1 was defined. You had a closed circle there. But on this problem, there is no closed circle on 1. So f of 1 is not defined, and the limit as x goes to 1 doesn't exist. So two things are causing this not to be continuous. But then from a visual standpoint, we should be able to recognize when we see something that looks like that, we're looking at a jump discontinuity. Let's look at our next graph. And so at this graph, we have an infinite discontinuity, and this discontinuity occurs when x equals 0. So an infinite discontinuity is also known as a vertical asymptote. And basically what you need to look for from a graphical standpoint is just when you get close to this value, again, for here, we're talking about x equals 0, the graph should shoot straight up towards infinity or shoot straight down towards negative infinity. Hits the term infinite. The graph is going to an infinite value from either the left and the right. It's either going to positive infinity or negative infinity. And a vertical asymptote, something you covered in the previous algebra class, what that means is the graph gets real close to x equals 0, but it'll never touch x equals 0. So this graph never touches x equals 0. So this also doesn't meet two conditions of continuity because x of 0 is not defined because, again, the graph of this function will never touch the line here at x equals 0. So x equals 0 is not defined. And of course, as well, obviously the limit doesn't exist. So the limit doesn't exist as well because it's going to infinity on the right and negative infinity on the left. So that is the whole deal. That's the graphical thing and what we look for discontinuities. Again, we have 3 discontinuities. A removable. When I see a removable, I should just see a little open circle on the graph. It could be an open circle or maybe a closed circle somewhere else on that same point, or it could just be an open circle without a closed circle on a point. Also, we know should be able to recognize a jump discontinuity and a jump discontinuity where the whole graph will jump from one value to another value at a particular x value. So there's a jump of the whole graph. And the last one is an infinite discontinuity, and an infinite discontinuity, what we'll see is occur is as x approaches a certain value, the graph shoots to either negative infinity or positive infinity from the left or the right. Okay, so those are our discontinuities. Now let's look at some example problems of the type of stuff we're going to be asked to do. All right, so we're just going to go through these examples, and these examples represent kind of two types of problems that we'll look at. The first one, they're going to give you a graph, so I'm going to read what it says. It says the graph of f of x is shown above. Describe the type of discontinuity that occurs at x equals 1, or classify it as continuous. So this is the point where you're trying to determine what type of discontinuity you're seeing, or else, perhaps it's continuous at that particular value. So let's look at this one. So this is when x is 1. So here is 1 right here. All right, so what do you think is happening here at x equals 1? So I'm pausing, giving you time to think. Okay, so hopefully you said there's a jump discontinuity there. See here's the graph, and then the whole graph jumps down here. So that is a jump discontinuity at x equals 1. And so our next examples, I'm going to be using the same graph and just going to ask about what's happening at different values for x. Okay, so question number 2, we're trying to see what happens when x equals 5. So here is 5 right here. Here is 5 right here. What would you classify this as? And hopefully you said removable discontinuity. This is a removable discontinuity. Whenever you just see a little open circle, the function basically stays the same, but you have this little open circle, whether it's a closed circle somewhere else on that same point. When you see that open circle, that's an example of a removable discontinuity. Our next one, we're talking about when x equals 3. So here's 3 here. And what do you think this one would be? So hopefully you said infinite. So this is an infinite discontinuity. And as you can see in the answer choices, jumps and infinite discontinuities are what are called non-removable discontinuities. And when we look at these from an algebraic standpoint, you'll get a somewhat of an understanding of why those two are non-removable and the other one is removable. All right, so this is definitely an infinite discontinuity. You know, the graph is shooting to infinity and negative infinity to the left or the right of the point. Let's look at another one. And this one, we're checking the value at x equals negative 0.5. Negative 0.5, that's right here. So what do you guys think? And again, hopefully you said removable. So this is the type of removable where it is the function, the point is defined, but you still have this open circle here, making it a removable discontinuity. And that's the last one on this graph. I just want to throw just a couple of things out to make sure, like if they asked about x equals negative 2, that would have been removable. If they said something like, what is it at x equals negative 3? Negative 3 would have been continuous. There's no open circle. So at x equals negative 3, f of negative 3 is 3. The limit as x goes to negative 3 is 3. So the value at the point is defined, the limit exists, and they're the same. So this is kind of what it looks like to be continuous. So basically when a function is continuous, just looking at the graph, I know we talked about being not continuous more than we talked about being continuous, but when you're continuous at a particular point, it should be smooth. Shouldn't be any open circles or any jumps or anything like that, just to be smooth. All these points right here, the function is continuous. The function is continuous at all these little points right here. But where you see this jump, where you see this open circle, where you see these vertical asymptotes, that's where the function is not continuous. Now the next set of problems are a little more involved, is on the same stuff, but we're going to classify a point as being continuous or not. And if it's not continuous, we're not going to name the type of discontinuity, but we're going to say what's making it not continuous. So we're going to say either the limit doesn't exist, or either it's not defined at the point, or maybe both of those things are happening, or maybe the limit exists and it's defined at the point, but they're not equal. So we're going to do that on these next set of problems. All right, so question 5, the question is f of x continuous at x equals negative 1? So this is negative 1 here. So let's deal with the easiest question first. Is it continuous? Would you say this is continuous at x equals negative 1? Hopefully you said yes. Why? What's f of negative 1? F of negative 1 is 4. What's the limit as x goes to negative 1 of f of x? The limit is 4. So f of negative 1 was defined. The limit as x went to negative 1 existed, and they were equal. So that is a yes for continuous. So again, when it's continuous, it should go smooth through the point. You shouldn't see any open circles or any jumps or anything like that. Let's look at the next problem. And all these will be on the same graph, just asking at different values again. All right, so the next one, we're checking continuity at x equals 2. So here's x equals 2 right here. So first question is it continuous at x equals 2? And hopefully you said no, there's a jump discontinuity. All right, so but it's not enough just to say it's not continuous. We have to say why it's not continuous. So let's go through our deal. Is f of negative 2 not defined? No, f of 2 actually is defined. F of 2 is negative 1, so it's not that. Is it that the limit as x goes to 2 of f of x does not exist? Yes, the limit doesn't exist there. It's negative 1 on the left and 5 on the right. So that one is not continuous because the limit does not exist. And I want to just go through the rest of the answer choices just so you're familiar what's going to be asked on this question, because I'm not going to look at all scenarios on this review. So just so you're kind of aware how all scenarios could be. So D is saying f of 2 is not defined and the limit doesn't exist. So these two are just for f of 2 not being defined or just the limit not existing. This one is for if f of 2 is not defined and the limit does not exist. And this one, E, is saying f of 2 exists and the limit exists, but they're not equal. So those are what all the answer choices say. So let's look at our last example. So the last example, we're checking continuity at x equals 4. So here's 4 right here. So again, the first question, is it continuous at 4? And hopefully you should say no. There's a removable discontinuity there. You have an open circle. There is a removable discontinuity. So let's see why it's not continuous. So let's go down the line. Is it because f of 4 is not defined? Absolutely, that's why it is. Look, f of 4 is not defined. So that is the only reason it's not continuous, because the limit exists. The limit is 2, but f of 4 was not defined. Okay, we'll stop there for lesson number 12, and we'll see you next time.